Welcome to section 10.7, direction angles and direction cosines. At the end of this section, we should be able to answer these questions. What are direction angles? What are direction cosines? What notation do we use to denote direction angles and direction cosines? And what properties are associated with direction cosines? Well, let's talk about direction angles. In a three-dimensional world, one angle isn't enough to give us a true direction for a vector. So what we need to do is actually describe our vector in terms of an angle off of each of our three separate axes, x, y, and z. We'll call the angle off of the x-axis alpha, and we can see that we'll draw that angle from the axis to our vector, just as I did there in the drawing. And then we will call the angle from the y-axis beta. And again, we'll go from the axis up to the angle. That will be beta. And finally, our last angle will be called gamma, and it looks kind of like a y. And you can see that we'll draw that from the z-axis over to the angle. Now, for each of those angles, we're going to work with one of their properties, the cosine. And we'll define each of those as C1 being the cosine of alpha, C2 being the cosine of beta, and C3 being the cosine of gamma. And the calculation to determine these direction cosines is simply taking the appropriate component of our given vector and dividing by the magnitude. So for C1, cosine of alpha, we take the I component of V and divide it by the magnitude of V. For C2, or the cosine of beta, we take the J component of V and divide it by the magnitude of V. And for C3, we take the cosine of gamma, which is going to be equal to the K component of V, divided by the magnitude of V. Now it turns out that there is a property that relates these direction cosines. We call it the Pythagorean property, because the sum of the squares of the direction cosines is equal to 1. So cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma equals 1. Or if we're going to use our C notation, C1 squared plus C2 squared plus C3 squared is equal to 1. So what does that mean? So this Pythagorean property leads us to another property. Since if we take those direction cosines, C1, C2, and C3, and place them as the components of a vector, that vector that we've created is a unit vector in the direction of the original vector. It will have a magnitude of 1, but point in the same direction as the original vector. Now remember that C1 is the I component of V divided by the magnitude of V. And C2 is the J component of V divided by the magnitude of V. And C3 being the K component of V divided by the magnitude of V. So let's look at this in practice. Here we have a vector V, 3I plus 7J plus 5K. And we're being asked to find the direction cosines and the direction angles for the vector. Well, to find the direction cosines, we simply take the components of our vector and divide them by the magnitude. So the first thing we need to do is to determine the magnitude. And here we pull out the super Pythagorean. So the magnitude of V will be 3 squared plus 7 squared plus 5 squared, which turns out to be 9 plus 49 plus 25, which turns out to be 34 plus 49, 83. So our C1 will be the I component 3 divided by the square root of 83. And our C2 will be the j component, 7 divided by the square root of 83. And our C3, or our direction cosine of gamma, will be 5 divided by the square root of 83. So to determine our angles, we need to take the inverse cosine of each of those direction cosines. So let's pull out our calculators. And we'll start with the inverse cosine of 3 over the square root of 83. Cosine of 3 divided by square root of 83. So our first angle is 70.774 degrees. Then we'll take the inverse cosine of the j component, so 7 over root 83. And we get 39.794 degrees. Then let's take the inverse cosine of 5 over the square root of 83. And we get 56.714 degrees. So there's our 70.774, our 39.794, and our 56.714 degrees. Here's another question. First we want to find the direction angles and the direction cosines of this new vector, 13I minus 6j plus 18k. First thing we need to do again is determine the magnitude of v. So magnitude of v is the square root of the sum of the squares, so 13 squared plus negative 6 squared plus 18 squared. Let's pull out our calculators for that one. It's a little impressive for mental math. So 13 squared plus 6 squared plus 18 squared gives me 529. Let's just see, second square root of the answer turns out to be a nice round number, 23. So that magnitude we determined to be 23. So our direction cosines, again, very straightforward. We just take the I component and divide it by our magnitude, so 13 over 23. Take the j component and divide it by our magnitude and get negative 6 over 23. And finally, our C3 is the k component, so 18 divided by 23. To find the direction angles, we need to take the inverse cosine of our ratio. So inverse cosine of 13 over 23. Beta will be the inverse cosine of the j component. So negative 6 over 23. And gamma will be the inverse cosine of the k component, or 18 over 23. I'll let you throw those into your calculator, and hopefully we came up with these angle measurements. 55.582, 105.121. Notice how beta is obtuse and our ratio was negative. And gamma is going to be 38.4999. So 38.5 roughly. Now, to write a unit vector in the direction of v, well, we simply take those three direction cosines and place them as the components of our vector. So our unit vector in the direction of v is simply 13 over 23 I minus 6 over 23 j plus 18 over 23 k. And there's our unit vector. Doesn't get much simpler than that. Okay, here's a third question. If alpha is 152 degrees and beta is 73 degrees, find gamma. All right, well, here we're going to use our Pythagorean property of direction cosines, where the sum of the squares of the cosines should be equal to 1. That tells me that the cosine squared of 152 degrees plus the cosine squared of 73 degrees plus the cosine squared of gamma is equal to 1. Let's find what the cosine squared of 152 degrees is and the cosine squared of 73 degrees. So let's pull out our calculators and figure out what the cosine squared of 152 degrees is. So the cosine of 152 degrees, and then we're going to square that, and we get 0.77959. And we're going to find the cosine of 73 degrees and square that. And then we're going to add those two numbers together and subtract them from 1. So we'll take that and add our last answer. And now we're going to subtract that from 1. So 1 minus our answer there. Now this value, 0.134922346, is equal to the cosine squared of gamma. So what we want to do is take the square root of this to find out what the cosine of gamma is. So second square root of that value. And so this number, 0.3673177, is the cosine of gamma. So we've determined that the cosine of gamma is 0.3673. But actually, remember that we arrived at that value by taking the square root, which means that when we take the square root, we have to remember that we could have a positive or negative value of 0.3673 to find the value for cosine squared of gamma, which means we could have two possible answers for gamma. So gamma will either be the inverse cosine of positive 0.3673 or the inverse cosine of negative 0.3673. If we take our calculator to find those values, we should find that gamma is either equal to 68.4497 when we use the positive 0.3673, or gamma will be 111.5502 degrees when we use the negative of 0.3673. So let's recap. What are direction angles? Well, direction angles are the angles that are formed with each of our coordinate axes from the vector. So alpha is our angle from the x-axis to our vector, beta is the angle from our y-axis to our vector, and gamma is our angle from the z-axis to our vector. What are direction cosines? Well, they are the cosines of those direction angles, as it says. And what notation do we use to denote direction angles and direction cosines? Well, for our direction angles, we use alpha, beta, and gamma. For our direction cosines, we use C1, C2, and C3. What properties are associated with these direction cosines? Well, we have two properties. The first is the Pythagorean property of direction cosines, where the cosine of alpha squared plus the cosine of beta squared plus the cosine of gamma squared is going to be equal to 1. Or, using our direction cosine notation, C1 squared plus C2 squared plus C3 squared equals 1. The second property that's associated with these concepts is the unit vector property of direction cosines. Our unit vector in the direction of an angle can be determined by determining the direction cosines of the original vector. We use those direction cosines to find the I, j, and k components of our unit vector. So cosine alpha is the I component of v divided by the magnitude of v, which is the same calculation we use for the unit vector.